Okay, good day. So this is hydraulics for civil engineering review. Let us first discuss the basic equation. So one of the first basic equation for hydraulics is the continuity equation. We are to discuss the fluid flow in conduits, let's say pipes. How do we describe that? Let's say this is Q, or the discharge. This is the area of, or cross-sectional area of the pipe multiplied by the velocity. So for example, we have pipes that are connected in series. For example, we have two pipes that are connected in series. Let's say this is discharge 1, then discharge number 2. If we are to follow the law of continuity, or that is the law of conservation of mass, discharge 1 will be equal to discharge 2, or that is the same as area 1 multiplied by velocity 1 is equal to area 2 multiplied by velocity 2. For example, we have pipes that are connected in parallel. For example, we have this source pipe, then it will branch out to two pipes. So let's say this is the discharge 1 and the discharge for pipe number 2 and discharge for pipe number 3. How do we write our continuity equation? That is, discharge in pipe number 1 will be equal to the summation of discharge 2 and discharge number 3. So this is one of the basic equation for hydraulics, the continuity equation. So let's have an example. One previous board exam in civil engineering. So a simple problem. A closed conduit with 25 centimeters diameter is connected to a 20 centimeters diameter pipe. If the velocity at the second pipe is 4 meters per second, what is the velocity at the first pipe? So this is a series connection. Let's say this is pipe number 1, then connected to pipe number 2. So the diameter of the first pipe is equal to 25 centimeters. Diameter of the second pipe is equal to 20 centimeters. We are looking for the velocity of flow in the first pipe, and we have the velocity of flow in the second pipe, that is equal to 4 meters per second. So this is discharge 1 is equal to discharge number 2. Or we can have it as area 1 B1 is equal to area 2 B sub 2. So what is the area of the first pipe? We have 0.25 in meters, 0.25 squared pi divided by 4 multiplied by B1 is equal to 0.20 squared pi divided by 4. This is multiplied by velocity at the second pipe is equal to 4 meters per second. So in this equation, we can cancel pi over 4. So let's compute for B1. So that is 0.25 squared. Alpha, or maybe we can use alpha. Alpha x is equal to 0.2 squared. Then the velocity at the second pipe is 4 meters per second. We are doing just zip solve. We have the velocity for the first pipe is equal to 2.56. We have B1 is equal to 2.56 meters per second. So on our choices, B1 is letter A, 2.56. We proceed to the next basic equation for hydraulics, that is the energy equation. Before that, we discuss what are the different energy heads. So we have the first one. Let's say this is the elevation head. In some references, they are using H. In some references, they are using Z. Then we have, after the elevation head, we have the pressure head. For the pressure head, how do we compute for the pressure head? We have basically pressure is equal to the unit weight times height. So how do we compute for this height? That height is equal to the pressure divided by the unit weight. Then the third one, this is for the velocity head. Okay, for velocity head, that is from potential energy to kinetic energy. So what is the equivalent of potential energy? This is the mass acceleration due to gravity times the height equal to kinetic energy. This is 1/2 of mass times the velocity squared. Okay, we are cancelling mass. Then we equate this to h. So what will be the equivalent? The equivalent of the velocity head will be that is equal to h is now equal to the v squared divided by 2g. So these are the three energy heads. So for example, we have this pipe, and let's say the direction of flow is from left to right, or let's say the direction of flow is downward to the right. Let's say this is Q. Okay, we are to consider 2 points. Let's say one end is 0.1, the second end is 0.2, and we are setting our datum line or reference line. So this height, let's say from our reference line to 0.1, let's say this is the elevation head of 0.1. On the top of the elevation head, so we have the pressure head at 0.1, that is the P1 over gamma. Then on the top of the pressure head, we have the velocity head, that is B sub 1 squared over 2g. So let's say this is the total energy head at 0.1. So let's say this is the E sub 1, the total energy head at 0.1. So the total energy head at 0.1 is basically equal to the total energy head at 0.2. But from Bernoulli's, so the energy head goes down with the direction of flow. So this is, let's say, the energy grade line. So again, the energy grade line goes down with the direction of flow. So this results to the head loss. Let's say this is the head loss or HL. So after the head loss, we have the velocity head at 0.2. This is B sub 2 squared over 2g. Then we have the pressure head at 0.2. Let's say P sub 2 over gamma. Then elevation of 0.2. So this let's say this total height is the total energy head. The total energy head at 0.2. Now we can now write our energy equation, that is from the law of conservation of energy. Energy at 0.1 is basically equal to the energy at 0.2. So what is the total energy head at 0.1? So we have that as, we have Z1 plus the pressure 1 over gamma plus the velocity head at 0.1, B1 squared over 2g. That will be equal to the total energy head at 0.2. We have the head loss plus the B sub 2 squared over 2g plus the pressure head at 0.2, the P sub 2 over gamma plus the elevation head at 0.2. So this will be one example on how we write our energy equation. So let's have one example. So let's have this example. A pipeline gradually enlarges from 300 millimeters in diameter at point A to 600 millimeters at point B. The velocity at A is 4.6 meters per second and the pressure at A is 270 kilopascals. Assuming that 1.2 meters of head is lost between A and B, determine the pressure at B if it be located 7.5 meters lower in elevation than A. So we have this given. So we have point A is higher than point B. So let's say the direction of flow is from A to B. Since the head loss from A to B is 1.2 meters, diameter at point A is 300 mm, pressure 270, velocity of flow is 4.6. We are looking for the pressure at point 2 or the pressure at point B. So let's first set as our reference line. Since we don't have elevation, let's say point B will be our reference line, and we set this point as elevation as 0. According to the problem, okay, point A is higher by 7.5 meters. So this will be our elevation at point A, or elevation at point 1. So again, above the elevation head, we have above the elevation head, we have the pressure head at 1. This is P1 over gamma. And then we have B1 squared over 2G. So the total energy head at point A is simply equal to the total energy head at point B. The energy grade line goes down with the direction of flow, so this will give us the head loss. And then we have the velocity head at point 2, B sub 2 squared over 2G. Then the pressure head at 2, P sub 2 over gamma. Then since we assume point B to be elevation 0, our C sub 2 is simply equal to 0. Then we write our equation. But we don't have yet B sub 2. We don't have yet the velocity of flow at point B. We are applying the basic equation, that is the continuity equation. That is the velocity or the discharge at point A is simply equal to the discharge at point B. We can have it as A1 B1 equal to area 2, okay, B sub 2. Then substitution, we have the area in meters. Again, we have that is 0.3 or 300 mm squared pi. This is divided by 4. B sub 1 is given as 4.6 meters per second. Area 2 is 0.6 squared pi divided by 4. Then multiplied by B sub 2. So again, we can cancel the pi over 4. Then let us compute. Okay, so solving for velocity number 2. That's equal to, we have B sub 2 is 1 point. We have B sub 2 is equal to 1.15 meters per second. Then, I think so our equation will be complete. We can now substitute to our energy equation. Okay, so let us write our energy equation. So starting again at point A on our first point, that is we have the elevation head at point A or point 1 plus the pressure head P1 over gamma plus the velocity head, that is the B1 squared over 2G. It will be equal to the total energy head at point B or on our second point. That is, we have the head loss plus the velocity head B sub 2 squared over 2G plus the pressure over gamma at point 2 plus the elevation head of point 2. So what is the elevation of point 1 or point A? We have that as 7.5 meters. Pressure at 1, it is given as 270 kilopascals. So this is divided by 9.81. Plus B1, it is given as 4.6 squared divided by twice of 9.81. Is equal to, okay, the given head loss is 1.2 meters from A to B. Plus the computed B sub 2, we have 1.15 squared. This is divided by twice of 9.81. Plus the unknown or the required, we have the pressure at 2 divided by gamma water, 9.81. Then plus elevation at point 2, this is assumed as to be the reference line or our elevation, 0. So computing for the pressure at point 2 or the pressure at point B, okay, 7.5 plus, we have 270, that is divided by gamma water, 9.81. Okay, then plus the velocity head at point 1, we have 4.6 squared. This is divided by twice of 9.81. This alpha equals, the head loss we have 1.2 plus The velocity head at point 2, we have 1.15 squared. This is divided by twice of 9.81. I plus, we have the unknown, so we set it as alpha x. Say alpha x. I divide by gamma water, we have 9.81. Again, we are just doing shift solve. So we have the pressure at point B is now equal to 341.721 kilopascals. Okay, so 341.721 kilopascals. So we check that on our choices. So we have that value. Okay, we have 341.7 kilopascals. So our answer will be letter A. Okay, so let's have this example. So for example, we have a pipe system with a pump. Water enters through a 500 millimeters diameter inlet pipe under a pressure of 15 kilopascals. It leaves through a 1000 millimeters diameter X-Hos pipe with a pressure of 5 kilopascals. If the center of the outlet pipe is 3 meters above the center of the inlet pipe and 500 liters of water passes a motor, or that is a pump. So let's say this is our illustration. Then according to the problem, so let's say we have point 2 as the X-Hos and point 1 as the inlet. So the X-Hos or point 2 is 3 meters above point 1. Okay, so first requirement, that is number 3, okay, determine the velocity of flow in the X-Hos pipe. That is our point 2. So for problem number 3, we are looking for velocity at point 2. So basically, discharge is equal to either discharge at point 1 or equal to discharge at point 2. So by law of continuity, 500 liters per second or 0.5 cubic meter. 0.5 cubic meter, diameter at point 2 is 1000 millimeters, or the same as 1 meter. So 1 squared pi divided by 4 multiplied by b sub 2. So our b sub 2 is equal to, that's the same as 0.5 times 4. 1 squared is the same as 1, so divided by shift pi. So we have, the velocity at point 2 is 0.6366, or we can have it as 0.637 meter per second. In our choices, let us check. 0.637, so the nearest value for number 3, we have letter C, that is 0.64. So that will be our answer for problem number 3. Number 4, I determine the head output supplied by the pump. So for the head output, we need to write or construct our energy equation. To construct our energy equation, we need to first compute for B sub 1. This is for question number 4. Okay, so we have discharge is equal to discharge at 1 and also equal to discharge at 2. So we have the discharge is equal to 0.5 cubic meter per second. Okay, the diameter of section 1 or the inlet is 500 millimeters. That is the same as 0.5 squared pi divided by 4 multiplied by b sub 1. So computing for velocity of flow at section 1, so that is 0.5 multiplied by 4, then divided by, we have 0.5 squared n pi. So we have velocity at section 1 is 2.546. So this is 2.546 meters per second. So this is velocity at 1, and required at number 3, velocity at 2. So let's have our diagram for the energy equation. So at section 1, since we don't have elevations again, so we assume this as elevation 0 And that makes a Z1 or the elevation head at point 1 to be 0. So above the elevation head, so we have the pressure head. Let's say this is the P1 over gamma. Okay, then above the pressure head, okay, we have the velocity head. So velocity head is B1 squared divided by 2g. So if we are to consider the distance from point 1 to the pump, supposedly I will be having a head loss. So let's say, okay, this is head loss, okay, number 1. So what is the purpose of the pump? Okay, the purpose of the pump will raise the energy head. So let's say this is the head output or the head added by the pump. Let's say 8 sub O. Okay, the total energy on the top of the pump will be equal to the total energy at point 2. So let's say this is another head loss since the energy grade line goes down with the direction of flow. So this is head loss number 2. Okay, that is for the distance from the pump to point number 2. Then after the head loss number 2, we had the velocity head at point 2, the B sub 2 squared over 2g. The pressure head at 2, that is the P sub 2 over gamma. And we have elevation of point 2 or the X-Hos pipe will be at Z equal to 3 meters. Okay, so how do we write our energy equation using this diagram? Okay, so starting at point 1, starting at point 1, so starting at point 1, we have that as elevation head at point 1. Okay, that is the C sub 1, okay, plus the pressure head at 1 is the P1 over gamma, plus the velocity at 1 is the B1 squared divided by 2g. Then again, supposedly we'll be having a head loss that is going down. The energy head goes down. So minus head loss number 1. Then it will be raised by the energy head added by the pump. So let's say this is plus, okay, plus the head output of the pump. This is plus 8 sub O. So the total energy head on the top of the pump will be equal to the total energy head at point 2. So our energy head at point 2, we have that is head loss number 2, okay, plus the B sub 2 squared divided by 2g plus the pressure head at 2, this is the P sub 2 over gamma, and lastly we have the elevation at point 2. Now all we have to do is, okay, we substitute. So what will be the value of the head losses? Okay, for this problem, okay, head loss is not given. Okay, no head losses are given. The next is we don't have the length of the pipe. Okay, so if these are the cases, we don't have a given head loss, we don't have the length of the pipe, okay, usually we assume head loss to be 0 for a board exam problem solving. So we assume head loss is equal to 0 for this case. So therefore, we have head loss 1 is 0. Head loss 1 is 0. Head loss 2 is equal to 0. Since our reference line is point 1, elevation 1 is also equal to 0. What is the pressure at point 1? On our given, the pressure at point 1 is equal to 15 kilopascals. So that is 15 divided by gamma water, 9.81. Okay, plus B sub 1, okay, the computed value is 2.546 squared. This is divided by twice of 9.81. Head loss 1 is 0, so this is plus the head output of the pump equal to 0 head loss number 2. Our B sub 2, the first requirement, that is 0.637 squared, okay, divided by twice of 9.81. Okay, plus the pressure at 2 is given as 5 meters, so 5 divided by gamma water. Then elevation of point 2, it is given as 3 meters. So in this equation, we are now computing for the head output of the pump. So that is 15, okay, divided by gamma water, 9.81. Okay, plus we have 2.546. This is squared, divided by twice of 9.81. Then plus the head output. Let's say we have that as alpha x equal to, we have velocity at 2, we have 0.637 squared. This is divided by twice of 9.81. Then is plus the pressure head at point 2. We have 5 over 9.81. Then lastly, that is plus elevation of point 2, that is 3 meters. Then we are doing ship solve. We have that value. The head output of the pump, question number 4, is equal to 1.671 meters. That's 1.6709. Let's have it as 1.671 meters. On our choices, we check on our choices. It's for number 4, we have letter A, that is 1.67. So sorry for that noise. We have letter A for number 4. And last question, we have number 5. Determine the required energy in horsepower to be supplied to the motor. So we have for number 5. So how do we compute for efficiency? We have for number 5, we have efficiency is equal to, let's say, the head output divided by the head input of the pipe or the pump. So the given efficiency is equal to 0.85%, or that is 0.85, 85% or 0.85, equal to our head output. The computed value is 1.671 meters divided by the head input. So what will be the value of the head input? That is 1.671 divided by 0.85. The value is equal to 1.966. 1.966 meters. Okay. So how do we compute for the power to be supplied? So that is the power input. We are computing for the power input. Okay, how do we compute for power? Basically, so we have the equivalent of power. Let's say this is P equal to the unit weight. If this is water, so we are using unit weight of water. The discharge, then multiplied by the head. If we are looking for the power input, then we are using the head input. And the required unit is in horsepower. We have gamma water, that is 9,000. We have 9,810. This is newtons per cubic meter. Then multiplying the discharge, it is given as 500 liters or 0.5 cubic meter per second. Then multiplied by the head input is equal to 1.966 meters. So the remaining unit, if we are to do unit analysis, for this one, if we are to do unit analysis, we are cancelling cubic meter. So the remaining unit is the same as, we have the Newton meter per second. This is the same as the watts. So to convert this one to horsepower, 1 horsepower is equal to 746 watts. Okay, so that we can have our final answer in the unit of horsepower. So we have the power input. Okay, the power input in horsepower. So that is the same as we have 9,810 newtons per cubic meter. Multiplied by the discharge, we have 0.5. Okay, the power input is the head input is 1.966. Okay, that will be in Newton meter per second. Okay, to be in horsepower divided by 746. And we'll be having a value of the power input in horsepower is 12.926. This is 12.926 horsepower. So let us check this value on our choices for problem number 5. Okay, so that is 12.9. For number 5, that is, okay, we have letter D. Okay, 12.9. So that will be our solution for problem 3 to 5. Okay, so this is an example for major losses with a pipe system with parallel connections. So we have a pipe network consists of pipeline 1, that is from A to B. Then at B is connected to pipelines 2 and 3, where it merges again at joint C to form a single pipeline for up to point D. Pipeline 1, so we have that is pipeline 1, pipeline 2, and pipeline 4 are in a series connection. Then we have pipeline 2 and 3 are parallel to each other. The rate of flow from A to B is 100 liters per second. And use F is equal to 0.02 for all pipes. So the given discharge, that is the Q1, or that is the flow for pipe number 1, that is from A to B. Our Q1 is equal to 100 liters per second, or that is basically equal to 0.1 cubic meter per second. Okay, we have the requirements. Number 6. Okay, compute the flow rate in pipeline number 2. So what will be our continuity equation? That will be discharge at pipeline number 1 will be equal to the discharge for pipeline number 2 plus the discharge in pipeline number 3. And that will be equal to the discharge in pipeline number 4. Okay, so when it comes to parallel pipes, so we have parallel pipes, that is pipeline number 2 and pipeline number 3. Okay, for parallel pipes, we have head losses are equal. So let's say the head loss for pipeline number 2 will be equal to the head loss in pipeline number 3. Okay, so we are using the Darcy-Weisbach equation, since this is, we have a given of a friction factor of 0.02. Okay, so we are using the Darcy-Weisbach equation for a major losses in pipes. So we can have the head loss, usually in references, we can have it as H sub F equal to, in terms of the velocity, this is the friction factor multiplied by the ratio of the length and the diameter, then multiplied by the velocity head, that is the B squared over 2G. Or we can also have the head loss in terms of the discharge equal to 0.0826. Friction factor, the length, the discharge squared, this is divided by the diameter. The diameter raised to 5. So we are using this in metric. If we are using cubic meters, for example. Okay. So again, if we have parallel pipes, the head losses are equal. So we can have head loss. Head loss number 2 is equal to head loss number 3. So what are the properties of pipeline number 2 and pipeline number 3? So we are using the discharge formula. Okay, for head loss number 3, that is, we have 0.0826. Friction factor is given as 0.02. What is the length for pipeline number 2? We have that as 2,200. Then discharge number 2 squared, okay, this is divided by diameter. What is the diameter of pipeline number 2? Okay, we have that as 300 millimeters or 0.3 raised to 5. Okay, then this value will be equal to head loss number 3. We have 0.08, 26. Friction factor is 0.02 for all pipes. Okay, what is the length for pipeline number? Okay, the length of pipeline number 3, that is equal to 3,000. Okay, we have that as 3,200. Then discharge number 3 squared, this is divided by the diameter of pipeline number 3. Pipeline number 3, we have 200 millimeters. So that is the same as 0.2 raised to 5. So we may cancel the common terms for both sides. The common terms for both sides of the equation, the 0.0826, 0.02. So now we are to express what is the equivalent of discharge number 3 in terms of discharge number 2. Okay, so we have that as we have 2,200 divided by 0.3 raised to 5, or maybe we should be using the calculator. Okay, so we'll be expressing the q sub 3 in terms of q sub 2. So let's have that as the square root of 2,200. That is divided by 0.3 raised to 5. Then I multiplied by 0.2. This is raised to 5. Divided by 3,200. Okay, so we'll be having the equivalent of q sub 3 in terms of q sub 2. Okay, so we'll be using 3 decimal places. Let's say we have 0.301. Okay, 0.301. Alright. So if we are now to go back on our basic equation, that is the continuity equation, the Q1 is equal to Q sub 2 plus Q sub 3. This is Q1 equal to the Q sub 2 plus Q sub 3. What is our Q sub 1? We have that as 100 liters per second. Alright, then Q sub 2 equal to Q sub 2, then plus equivalent of Q sub 3 is equal to 0.301 of Q sub 2. We just substitute the equivalent of Q sub 3. So solving for Q sub 2, okay, that is equal to 100 equal to alpha x for discharge in pipeline number 2 plus 0.301 of alpha x. Then shift solve. Okay, we have the discharge in pipeline number 2 is now equal to, we have 76.864. 76.864 liters per second. So on our choices, we check that value. We have 76.864. So the pipeline or the flow in pipeline number 2, 76.84. The nearest value is equal to 76.9. So rounded to 76.9. Then question number 7, compute the flow rate in pipeline number 3. Okay, how do we compute for pipeline number 3? Okay, again, we are using our continuity equation. Pipeline number 1, flow rate is equal to 100 liters per second equal to, we are able to compute for discharge number 2, that is 76.864. So plus the discharge in pipeline number 3. So computing for the discharge in pipeline number 3, we have 100 minus 76.864. So we have that as Okay, 23.136 equal to 23.136. This is in terms of the liters per second. So we have these values, Q2 and Q3. So let us check this value in our choices. Okay, problem number 7. So 23.136, or we have that as letter A, rounded to 23.1. That will be our answer for problem number 7. Okay, so this is for question number 8. Compute the total head loss from A to D. So we are considering 3 head losses for this case. That is the head loss for pipeline number 1. Let's say this is head loss 1. Then, for parallel pipes, we are just considering 1 head loss. So it's either we are using head loss 2 or head loss number 3. So we are using just 1. Then for the last pipeline, that will be the head loss for pipeline number 4. Then let's have our main equation. So our total head loss, the total head loss will be equal to the head loss for pipeline number 1 plus the head loss for pipeline number 3 or the head loss for pipeline number 2. Then last, we are adding the head loss for pipeline number 4. So we are using the head loss equation in terms of the discharge. That is the head loss equal to 0.0826 friction factor, the length, the discharge squared, divided by the pipe's diameter raised to 5. So let's have head loss 1. Head loss 1 is equal to 0.0826. Friction factor for all pipes is 0.02. What is the length of pipeline number 1? So pipeline number 1 is 3,000 meters in length. The discharge is 100 liters per second or 0.1 cubic meter per second. Squared, this is divided by the diameter. Diameter per pipeline number 1 is 200 millimeters or 0.2 raised to 5. We have head loss number 1. That is 0.0826. Multiplied by 0.02. We have its length equal to 3,000 meters. Multiplied by the discharge, that is 0.1 squared. This is divided by the diameter is 0.2 raised to 5. Head loss number 1 is 154.875. So that's equal to 154.875 meters. Well, that is for pipeline number 1. So we proceed to pipeline number 2. We have head loss for pipeline number 2 is equal to 0.0826. Friction factor is 0.02. The length per pipeline number 2 is equal to 2,200 meters. The discharge, we are able to compute for the discharge, that is equal to in terms of liters per second, this is 76.864. Or if we are to convert this one, divided by 1,000 liters, we'll be having 0.07686 cubic meter per second. If I to use only 3 decimal places, let's say 0.0769 cubic meter per second. Okay, so we substitute. Let's say the discharge for pipeline number 2 is 0.0769 squared. This is divided by the diameter. Diameter for pipeline number 2 is 300 millimeters. So this is 0.3 raised to 5. We have that as 0.0826. Friction factor is 0.02. Then the length for pipeline number 2 is 2,200. The discharge is 0.0769. This is squared. Divided by the diameter, we have 0.3 raised to 5. So 8.845 meters. Head loss number 2 is equal to 8.845 meters. Okay, so this will be our head loss for pipeline number 2. Okay, 8.845. Okay, then we have for pipeline number 3, so for the last pipeline, let's say this is head loss for pipeline number 3 is now equal to 0.0826. Friction factor for all pipes is 0.02. What is the length for pipeline? Supposedly it's not pipeline number 3. We are using pipeline number 4. Since the discharge for pipeline number 2 is equal to the discharge, the head loss for pipeline number 2 is equal to the head loss in pipeline number 3. Head loss number 4, 0.0826, friction factor 0.02. The length of pipeline number 4 is equal to 2,800. So the pipes 2 and 3 merges again to form pipeline number 4. So we go back with the discharge of 0.1. So 0.1 squared divided by the diameter for pipeline number 4 is 400 millimeters, or 0.4. This is raised to 5. So we have 0.0826. Okay, friction factor is 0.02. Okay, the length for pipeline number 4 is 2,800. Okay, then discharge. Okay, the pipes merges again. So we'll be having a discharge of 0.1 squared. Diameter of pipeline number 4 is 400 millimeters or 0.4 meter. Okay, we have the discharge equal to 4.517. So let's say head loss number 4 is equal to 4.517 meters. Okay, so we are now computing for the total head loss. So total head loss, this is from A to D. Head loss 1 is 154.875 meters. Head loss 2 basically equal to head loss number 3, that is 8.845 meters, plus head loss 4, we have 4.517 meters. So we'll be having the total head loss is now equal to that is 154.875 plus 8.845, then plus 4.517. We have 168.237. 168.237 meters. This is the total head loss from A to D. Considering for parallel pipes, we have only one head loss. So we check this value on our choices. So that is 168.235, the closest value on our choices. That will be letter A. So this will be our solution for problem 6, 7, and 8. So major losses, considering are using the Darcy-Weisbach equation. I will proceed to another equation for major losses. That is the Hazen-Williams. Okay, for Hazen-Williams formula, we may express the head loss. In some references, they are using H sub C. This is equal to 10.67 multiplied by the length. The discharge, this is raised to 1.85 all over. Okay, we have C, that is the pipe constant or the Hazen-Williams coefficient, raised to 1.85. Then the pipe's diameter raised to 4.87. So let's have this past board exam problem in civil engineering board exam. Okay, so a hydroelectric power generating system is as shown. Water flows from an upper reservoir to lower one, passing through a turbine at the rate of 1.5 liters per second. The total length of the pipe connecting the two reservoirs is 100 meters. The pipe diameter is 250 millimeters and the Hazen-Williams coefficient is 120. Okay, The elevations of reservoirs 1 and 2 are 197 meters and 50 meters respectively. Alright, so let's have that figure. So let's say we're using a bigger one. Okay, so we have two reservoirs. So elevation of the higher reservoir is 197. Then elevation of the lower one is 50 meters. So we have the given discharge, okay, or the flow, rate of flow is equal to, okay, we have 150 liters per, 150 liters per second. Or we are to convert this one to cubic meter. This is multiplied by 1 cubic meter is equivalent to 1,000 liters. So this is the same as 0.15 cubic, the cubic meter per second. Okay. So the first requirement is a very simple question. I determine the velocity in the pipe. So basically we have discharge is equal to area times velocity. We have the discharge is 0.15 equal to area. What is the pipe's diameter? The pipe's diameter is 250 mm. Or in meter, that is 0.25 squared pi. This is divided by 4, then multiplied by the velocity. This is for question number 9. So we are computing for the velocity. So we have 0.15 is equal to 0.25 squared sheep pi. This is divided by 4, then multiplied by the velocity, let's say alpha x, then shift solve. So the velocity is equal to, we have 3.05, 6, let's say 3.05, 6 meters per second. If we are to use 3 decimal places. So if we are to check on our choices, 3.056 for question number 9, that is letter, we have letter A, 3.056 meters per second. Then question number 10 is compute the total head loss in, compute the total frictional head loss in the pipe. So that will be the time that we are going to use our formula. So we have for question number 10, this is for question number 10, how do we compute for head loss using the Hazen-Williams formula. This is the H sub C is equal to 10.67 multiplied by the length, the discharge raised to 1.85 divided by the Hazen-Williams coefficient or the pipe constancy raised to 1.85, the pipe diameter raised to 4.87. So we'll be having the head loss due to friction. This is equal to 10.67 substitution. What is the total length of the pipe? The length of the pipe is equal to, we have 100 meters. So this is multiplied by 100 meters. The discharge is given as 0.15 cubic meter per second. So this is all over. The pipe constant or the Hazen-Williams constant is 120 raised to 1.85. The pipe diameter is 250 mm or 0.25 meter. This is raised to 4.87. So we are now computing for the head loss due to friction. That is 10.67. This is multiplied by the length of the pipe is 100 meters. Then the discharge is 0.15. This is raised to 1.85 all over. The pipe constant is 120 raised to 1.85. Then multiplied by the pipe's diameter 0.25 raised to 4.87, and that will be equal to, we have 3.886 if you are to use 3 decimal places. So the discharge is equal to 3.886 meters. If you are to, so 3.886. So we check this value on our choices, the 3.886 meters. Okay, on our choices, the closest value, okay, we may assume that it is rounded to letter C. We have 3 point, right, that is 3.9 meters for letter C. That will be our answer for question number 10. For question number 11, compute the power generated by the turbine in kilowatts. So, to compute for that power generated by the turbine, we need to determine the head extracted by the turbine. And we can use the energy equation. So let's say this lower reservoir as our reference. Okay, we'll be having the difference in elevation. Or we have the elevation heads already. So the elevation for 0.1, let's say this is the upper reservoir is 0.1 and lower reservoir will be 0.2. Elevation of first reservoir is 197. Elevation of the second reservoir or the lower reservoir is 50 meters. Okay, so take note, if we are dealing with reservoirs, it is a large surface area of water exposed to atmosphere. So we assume that the pressure head will be equal to 0. Okay, for both reservoirs. So P sub 1 equal to 0, P sub 2 is also equal to 0. It is a large area of water or a large body of water. So even though we are allowing discharge, okay, we assume that the liquid surface will not move. So if it is not moving, we assume that the initial velocities or velocities of water will be 0 for both reservoirs. So if we are to consider the total head loss is basically the difference in elevation of the two reservoirs. We can prove that by writing our energy equation. That is the elevation head at 0.1 plus the pressure head at 0.1, okay, plus the velocity head at 0.1 will be equal to the head loss plus the velocity head at 0.2, b sub 2 squared over 2g, plus the p sub 2 over, that's the p sub 2 over gamma, plus the elevation of the second reservoir. So again, for reservoirs, pressure is equal to 0, velocity is equal to 0. So if we are to compute for the head loss, so basically we have head loss is simply equal to elevation of the first reservoir minus the elevation of the second reservoir. So basically the difference in elevation. So if we are now to compute for the total head loss, that is equal to elevation of 0.1, that is 197 minus 50 meters. So the total head loss will now be equal to 147 meters. So that will be the total head loss. But for this case, if we are to consider what are the components of this head loss, okay, we are considering two components for this problem. Okay, the first component of this head loss, that is the head loss due to friction using Hayes-Williams, that is the H sub C. Take note, we have a turbine. So turbine acts oppositely as a pump. So if pump adds up the head, or if pump will raise the head or the energy head, so turbine will extract a head, or that is considered to be a head loss. So the head loss extracted by the turbine, let's say H sub T. So the equivalent of our total head loss for this case, the total head loss will be having two components. That is the head loss extracted by the turbine plus the head loss due to friction, the H sub C. So we have the head loss equal to 147 meters equal to the head extracted by the turbine plus frictional head loss, that is equal to 3.886 meters. So let's have the total head loss. Okay, our total head loss is equal to, not the total head loss, this is the head extracted by the turbine. 147 minus 3.88, that's 3.886. Okay, we have the head extracted by the turbine is equal to 143.114. So 143.114 meters. Okay, the head extracted by the turbine. So this is for question number 11. How do we compute power for power? That is equal to the unit weight of water, the discharge, then multiplied by the head. If we are computing for the power extracted by the turbine, we are or the power generated by the turbine, we are using the head extracted by the turbine. So this is equal to, gamma water is 9.81 kilonewtons per cubic meter. We have a discharge of 0.15, that is in terms of cubic meter per second. The head extracted by the turbine is equal to 143.114 meters. If you are to do unit analysis, cancelling cubic meter, okay, what will be the power generated by the turbine? Remaining units will be kilonewton meter per second. Kilonewton meter per second is the same as the kilowatts. So we compute for that value. So we have gamma water is 9.81 multiplied by the discharge 0.15. The head extracted by the turbine is 143.114. So we have 210.592. So this is 210.592 kilowatts, or the kilonewtons per cubic meter. So we check this value in our choices. So 210.592, the closest value in our choices is we have letter A, 210.6 kilowatts. So this will be our solution, okay, for problem 9 to 11. So this is a major head loss formula, that is the Hazen-Williams.